Hello, my name is Professor Joungho Kim at Terabyte Interconnection and Packaging Laboratory at KAIST. I'm glad to meet you at this WPTC 2020. The title of my presentation will be Machine Learning Methodologies and Metamaterials for High Efficiency and Low EMI Wireless Power Transfer Designs. Machine learning and metamaterials might be a little bit strange subjects to most of the engineers and scientists in wireless power transfer societies. However, I'd like to introduce these new methodologies which may be very useful for your design works. These researches are currently going on in my laboratory, and I would like to give you shortly the concepts, approaches, and initial research results today. This slide shows the outline of my presentation today. I will start with introduction of machine learning. In this section, I will give you the basic concepts of machine learning and the future directions. And then I will give you an examples to show that it is very useful methodologies for wireless power transfer system design. In the next session, I'd like to talk briefly about metamaterials. It is a kind of artificial materials which is not present in natural world. And then I'm gonna give you examples at the next sessions. Finally, I will give you future directions and conclusions. This slide shows very basic concepts of machine learning. Machine learning means it is a kind of new artificial intelligence methodology that represent the human brain activities into the computer world. On the right side, it shows the layered structures of neural network. It has an input vector and output vector. In between input layers and output layers, there are number of hidden layers. Usually, the number of hidden layers is more than 100 or 200. Now it is getting deeper and deeper. Input layer is actually a vector. It could be a one-dimensional vector, or it could be two-dimensional vector, or it could be n-dimensional vector. N-dimensional vector is usually described as a tensor. And the output layer is, of course, a vector. Sometimes input vector is a picture. Output vector classifies whether it is tiger or cat. In each layer, there are millions of cells. Each cell represents a memory in the computer. The connection between previous layer and next layer is connected with these arrows. This arrow means this distal number of this cell is connected to next cell, and that is multiplied by the weight, actual number. So each arrows has different strengths of connections. And then at a cell in the hidden layer, it is summarized, added all together. And if the added number is larger than a certain threshold number, then the number is propagated to the next cells in the next layers. So signal is propagating along the input layer to hidden layer, and final layer along these arrows. That is called propagation. At the final gate, if the answer is not correct, this weight and connection should be upgraded. That operation is called backpropagation. So having this propagation and backpropagation during the training session usually this number of training is thousands and millions. If we have more and more big data, the number of the iteration and training session will increase. And the accuracy and efficiency of this brain is usually becoming higher if you have more and more training session with more and more big data. Of course, each cell represents a memory, and this computing, the connection and added operation and training session will be done by GPU. So computer and semiconductor devices are actually doing this training work. These are basic concepts of neural network, and especially when this AI is being trained using the data. Usually in the traditional artificial intelligence, we teach them using our mathematics or our logics. But in this case, these neural networks are learning by themselves using the big data. So actually data is becoming a textbook. That kind of neural network is called machine learning. Today, in my presentation, I'm gonna use the machine learning methodologies for wireless power transfer system. Why this AI is becoming so powerful in these days? I think there are three factors. Number one is because this machine learning is learning based on the big data. Big data is very important. We are having more and more big data because of the internet and smartphone and cameras. And even YouTube and Netflix are supplying big data for us for artificial intelligence. Recently, this data is also generated in the computer, especially in virtual computer world. So we will see more and more data will be accumulated in the internet society, in this digital transformation world. That means that AI will become more and more smarter. And deep learning algorithm is also important factor. And another important factor that enables artificial intelligence is that we have more computing power in the clouding system. Especially GPU and DRAM performance is rapidly increasing. And because of that, we have this artificial intelligence right now. I would like to shortly talk about the values of artificial intelligence. At the beginning, it will work for us. They will replace our brain activities. So we don't need to work. So we can spend more time for our physical activities or travels or hobby. So AI can save our time, labor, resources, and capital and energy. So it will give some time for human for creative activities. So it will improve our human life. But also, in addition to that, it will give us freedom from labor and nature. That is a good aspect of artificial intelligence. Each unit cell in this neural network is called perceptron. In the perceptron, in the computer program, a previous layer of digital numbers in the vector is multiplied with the weight number, and it is summarized. If the summarized number is higher than such a threshold number, it will go through the output. This unit vector, unit element is called perceptron. And also when we are designing this machine learning networks, it is important to determine what kind of mathematical expressions we are going to use for activation functions. Very simple, easy methodology is linear function, and another is logistic function. And as you can see in this slide, at certain range, it is a linear, but if the input number is over a certain threshold number, will be a 1, or otherwise it will be 0. So it is a kind of step function. And also another type of step function is hyperbolic tangent function, and it is also sometimes used. So when you are designing artificial intelligence machine learning network, you should be carefully determining this activation function. Of course, these numbers, weight numbers, will be determined during the training session. As I mentioned before, this is very simplified machine learning neural network. Is the input vector, hidden layer 1, hidden layer 2, and output layer. As I said before, input vector could be a two-dimensional picture. Output could be one-dimensional vector that describes whether it is tiger or cat. It gives us probability of tiger or probability of cat. And if we show them a picture, the signal propagate, and each circle represents the perceptron, and it is connected to the output layer, and output layer will give you what kind of identity it has. It is called forward propagation. If the answer is wrong during the training session, then we have to correct this connectivity and weight numbers. And that correction process is called backpropagation. During the backpropagation, we update the weight numbers using the gradient descent methodologies. During this backpropagation, when we have errors, we have to correct that connections and weight numbers. That is called training and backpropagation. We have to estimate how much we have to give the computer some certain way that it can determine how much error it has. That is called error function or cost function. This is our right answer, and this is our answer from the machine learning during the training session. If the error is bigger, the number will be bigger. That this kind of simple error function or cost function is called a mean square error function. And there are many different type of cost function representation. Sometimes we are using logarithm function, and sometimes we can use entropy functions. Sometimes we can use these linear functions. There are many different type of functions. And when you are designing the machine learning network, you have to decide this cost function as well. During the training session, you have to, your network should be upgraded. And at certain point, the error will be minimized. Usually at this point, the gradient differentiation of this cost function should be 0. So during the backpropagation process, we are using the differentiation method that is called the gradient descent. We measure the gradient at each cost function at each point, and we update the weight values until gradient is becoming 0. That conceptually that is called gradient descent. And so training of the machine learning means that we are trying to find this weight number, the A and B, to be a certain weight number, then we can minimize the error. That is the end of training session in machine learning. There are many different types of neural network. One of the very popular network is convolutional neural network, and it appears about 10 years ago. It is very popular at this moment, and a little bit complicated than the deep neural network. In each layer, we have a map, and we have two-dimensional data, and it has also multi-dimensional with multiple depth. And if we have input vector, some certain area will be mapped to a point at the next matrix, at the next layer. And to minimize the computer memory and the computations, sometimes certain area will be summarized, or only we pick up the maximum number. That is called maximum pooling. After 200 or 300 layers of this convolution process and max pooling process, finally it has fully connected layers, and it is connected to the final vector. So at the final vectors, we will, if we give them a picture, they will say us the probability of bird is 90.99%, probability of sunset is 10%, probability dog is 1%, probability cat is 1%. And so they will give us the probability distributions. We usually pick up the highest probability for the right answer. And this is very popular network, most popular network in machine learning area. Recently also we have a neural network called the Generative Advisory Network. It has capability to make an art, music or drawing or literature and whatever. And this is one of the examples of the that machine learning is called GAN, Generative Advisory Network. And this machine learning actually draw a picture of KAIST campus. And when we are doing the training session, we show them a lot of cohorts pictures, cohorts drawing, and they learn a lot of cohorts drawing. Then if I show KAIST picture, they actually this GAN machine learning network actually produce this artwork that is the description of KAIST library with cohort painting. So it means that machine learning can do the very clear classifications, and also they can do a lot of works. At the same time, they can do the creative work. I think this is a very simple description of future AI machine learning for human brain. Right now, some of neural network can replace our eye. That kind of neural network is called convolution neural network. And some neural network can speech. They can replace our mouth. And those kind of network can be called LSTM, or recently transformer learning. Is very powerful neural network who can speak and who can write. Also, there might be some neural network that can listen that can be called recurrent neural network. So at this moment, each neural network replaces a certain part of our brain. However, in some years later, it will be combined together to become a single neural network. So single neural network will represent our body, and one person in the universe, in the earth, there might be 100 millions in earth, and each person will be represented by a neural network in computers. And of course, in order to achieve that, we need very high powerful computers and memory devices, and also with the minimal power consumption. In addition to this multimodal neural network, we can train them using the different data. So by having training of many different data, they will have emotions and ethics and images and religions. So then by combining this kind of human nature with this kind of functionalities, I think that kind of neural network can be called as artificial general intelligence. Now let's move on to the next session. I would like to talk about what could be next direction. And one possibility is that AI will replace our engineering work. So this kind of, I would say this kind of work is called AI engineering. And this capability and function can be embedded to the CAD softwares for design works. This is sad or happy for us, but if engineers can efficiently use these AI engineering tools, we can save our time as well. And currently, I'm thinking about what kind of activities the AI can do for us, especially for AI engineering. They can do estimation. We are spending a lot of time and computer resources for simulations to estimate the performance, such as the time domain waveform, frequency domain responses, and efficiencies and field distributions. And there are a lot of work is going on, and we have to do a lot of resources and time to do the computer simulation. Probably AI can do that for us. very short time. And another work I think AI can do is a problem source analysis. Sometimes you have certain problems in your design, AI can find the solution. Right now, very experienced designer can do that, but in the future, AI can do for us. Another work for AI can do for us is the design optimization. At a certain point, we give them tasks and we give them target and they can finalize the design to meet the specification. Right now, actually engineers and computer simulation will do that, and it will take a lot of time and resources, and AI can do that. Application could be circuit, antenna, coil, PCB, integrated circuit design, and architecture design. The benefit of AI engineering could be we can save the time and cost, design accuracy and efficiency can be improved, and finally, at some point, this AI can replace the engineering resources. This is the conceptual figure of the machine learning for our design works, engineering work. For example, we can design the semiconductor interconnections at the IC level or package level or PCB level. And sometimes we want to estimate the eye diagram to qualify, to estimate the qualification of the interconnection. That is called eye diagram. And we spend a lot of computing time for eye height and eye width estimation. But if we have certain data of design and eye diagrams, if we have already that, we can train them into the deep neural network. And if they are trained very well, they don't need to do the simulation. They will immediately calculate this eye diagram simulation. So as I mentioned in the previous slide, AI can do the estimation for us. And then if we have this deep neural network, which is trained using this computer generated data, if we give the input parameters, immediately it can estimate the output. We don't need to have all the simulations. Right now, in our computers, we have the softwares, CAD softwares. In that, with FDTD or many different algorithms to do to achieve very complicated simulations. Sometimes the dimensional variance is huge from nanometer to meter range. Also, we have to achieve multi-physics. Sometimes we have to do the electromagnetic simulation, circuit simulation, as well as thermal simulation, mechanical simulation. Very complicated work. And also number of the devices to be simulated will be the millions or billions. So sometimes it takes a lot of time. So if we have a deep neural network, they can do those estimation immediately. It will improve our work efficiency. For example, this is the interconnections, and this is actual simulations. And our deep neural network estimation, this number, and this is actually full wave simulation using the computer. And accuracy is significantly small. The difference is small, less than about 1% or 0.1%. But however, computational time of conventional 3D simulation takes 1 hour and 3 minutes, but our deep neural network takes just 1.7 seconds. So at some point, I'm sure this deep neural machine learning technique will be very useful for engineering work, including wireless power transfer system design. Actually, we have many different test data. So we have to finally evaluate how much accuracy our deep neural network it is. And this solid line is the case of simulation, full 3D simulation, and the deep triangle means our neural network calculations. You can see for those 60 cases, the accuracy is quite good, very nice. And however, surprisingly, for all those cases using the simulation, it takes 63 hours for 60 test set verifications, but it takes just 1.7 seconds. Surprisingly useful. Also, we applied this methodology for IC design. PDN means the power distribution network, and we gave them the red line, that's the target impedance. And we found that we designed a neural network that is called the reinforcement learning. Reinforcement learning is they are doing the optimization by themselves. AI are doing by themselves. We are not touching anything. We just give them target number, target functions, and it automatically, machine learning automatically design this package and chip inductance capacitance to meet this PDN impedance target. So as I mentioned before, machine learning can do the estimation work, source finding, and optimization work. Today, my speech time is limited and I cannot show all of them, but definitely I think we are going into the direction of machine learning is becoming very important tool for our engineers. And this machine learning is doing during the training session. Initially, when they learn a little bit, and you see that this line, this solid line, very large impedance and resonance peaks. However, after 16 of training session, it is gradually becoming very low impedance under the target line of red dotted line. And I'm saying that this is not done by human being. This is done by computers. And the algorithm is the machine learning, specifically reinforcement learning. So what I'm saying is this kind of learning algorithm, estimation, and optimization can be also applied to wireless power training system. And in the wireless power transfer system, coil design is a very basic start. And always, of course, there are many different factors to when we are designing wireless power transfer system. For example, power supply and inverters and rectifiers, and also matching circuits, and also ferrite and shielding. There are many different design tasks. But in this case, I'm giving you one example in which that we can also use the machine learning when we are doing the core design. And usually when we design a coil, then we can do a lot of simulations. And if we have certain amount of data sets for these cases, we can use this coil design and results such as the time and frequency domain response and efficiency. We can use this data for deep neural network training. In this case, if we have a good training, then if give them some certain core design, eventually give some efficiency. So the computational time will be very effectively reduced. And we give them some certain cases. For example, when we are designing the coil using the PCB, we have to decide the width, space, number of layers, and number of turns. And when for this demonstration, we choose the frequency 6.78 megahertz. And initially, we define the target system, and then also in the next step, we define the target parameters such as width, space, number of turns, and number of layers. And we calculate the efficiency of wireless power transfer system. Initially, we generate the data using the 3D EM simulations and circuit simulation. And after certain accumulation of data, of course, it takes some time and resources. Then the DNN training is done. And then we develop the DNN model. This is case, we are trying to estimate the efficiency of wireless power transfer system. Sometimes, depending on your design, it could be nearly 100% or 95%. Or sometimes if your design is not correct because of resonance frequency changes and certain things, and efficiency will be very low. And for the case of 40 different test sets, you can see very close agreement between the our machine learning model and this computer simulations. Of course, usually for the computer simulation, it takes 8 hours, but our deep neural network DNN model takes just 40 seconds. So it is another example that we can apply this artificial neural network machine learning methodology for design optimization and design estimation. And of course, in the future, a wireless power transfer system will be useful for hearing aid charger or implanted device chargers and so on, in addition to the smartphone. And I think the in the designing during the design process of this wireless power transfer system, I think deep neural network will be very useful methodology. Now I'm going to shortly talk about metamaterials. In our world, we have 4 different materials. In nature world, we have material who has the higher, larger than zero permittivity and larger than zero magnetic permeabilities. But in some case, some material has double negative material who has the less than zero electric permittivity and magnetic susceptibilities. And now we are going to work on this area in which magnetic permeability is less than zero. In natural world, we don't have this material. Natural world, we have magnetic permeability is usually 1 or larger than 1. Some material like ferrite, it has very higher number. Then we can confine the magnetic field into the circuitinator, so we can use it for shielding purpose in wireless power transfer system. But sometimes my imagination is saying that we may need a magnetic permeability material who has the negative number. And actually, we designed some material using the printed circuit board in which in the central area, we have metamaterial at certain frequency, not all frequency, but at certain frequency, it has magnetic permeability is almost becoming a 0. Then whatever direction of the magnetic field incident to this material, then it will be the next, the magnetic permeability, magnetic field direction will be vertical. Whatever angle of incident, it is the outgoing angle will be vertical. So we can use this material who has the magnetic permeability is equal to 0. Also, we can design a magnetic material who has negative magnetic permeability. Then even though incident angle is this positive directions, but outgoing magnetic field angle is negative. So usually if this mu2 is positive, you will usually have another positive angle, but it is another angle. So by having these two, combining these two material of metamaterial, we can confine magnetic material at the center of this PCB. That is the main idea. For example, if we have two material, TX coil and RX coil, if we put this hybrid metamaterial slab between them, then initially the magnetic field will diverge to the outside because of Gauss law and Maxwell equation probability. And this is the divergence law of magnetic field. But however, if we have metamaterials, then it has a 0 magnetic permeability or minus magnetic permeabilities. It will have a lens effect. Magnetic field will be curved into the minus angle, and it will help to enhance more magnetic field coupling to the RX coil. Then it can enhance the magnetic coupling coefficient. Then it will enhance the power transfer efficiency from TX coil to RX coil. That is the idea of our own. And actually, we actually made this metamaterial in the central 9 component. It has the magnetic permeability of 0, and also the another layer is the magnetic permeability of negative numbers. And we did the measurement, and you see that at certain frequency of 6.84 megahertz, efficiency was improved to 60%, more than 60% at a case of 15 centimeter distance. So this is the amazing achievement. So our idea is that in the natural world, there are certain materials, air and dielectric and ferrite, that is useful for certain applications in wireless power transfer system. But however, we can make artificial materials. So today our two subjects is artificial material and artificial intelligence. And using this artificial material that is called metamaterial, in which metamaterial has negative or 0 magnetic permeability at certain frequency, not all the frequencies, but if we design this metamaterial well at those frequencies, we can utilize those properties of zero and negative magnetic permeability. This is the conclusion of my presentation. So wireless power transfer system design is a kind of traditional engineering work. We are using the electromagnetic field calculations and circuit calculations, device physics. We combine all of them together to make a maximum efficiency with the minimum EMI. And sometimes we are using the ferrite material to achieve that purpose. What I'm saying is that that's not our limit. We can apply the new methodologies such as the machine learning, and machine learning will give us some fast and accuracy design and optimizations. And in order to do that, we need some fast computers. Probably quantum computing will help us. And also we have new material called metamaterials. So what I'm saying is combining machine learning, quantum computing, and metamaterials, we can enhance our wireless power transfer world, efficiency, EMI safety, and so on. And by combining these two, someday we can use this wireless power transfer system for medical devices. And also we can achieve our dream to supply the power, electrical power, to any time, anywhere. That's the end of my presentation. Thank you for your kind of attention.